Hey, fabulous students. Welcome to second semester, day one. I think this is assignment 5 on the assignment calendar. And I actually wanted to say welcome back. And maybe we could take a look at a little review of some stuff from last semester. Well, of chapter 6. Because I worry that you've forgotten about some of it. And I need you not to. Pounds of lint per hour. So our input is hours, 1, 3, 7, and pounds of lint per hour that grow in your navel. It's from wearing all those winter sweaters. All right. So 1, please find LRAM. And 2, don't forget your units on that answer. Pause the video, give it a try. Welcome back. So LRAM, remember, uses the left side of those rectangles. And you could certainly take the time to graph this. It's just that graphing this takes a while. And then we've got boink, boink, boink. And so we're saying, okay, I got some rectangles. If I'm doing LRAM, I'm coming this way. And so this area is, I've got a width of 1 minus 0, and the height here is 1/2. So 1/2 times 1 is 1/2. And then here, I'm going from 1 to 3, so 3 minus 1, and the height here is 2. So I've got 2 times 2 or 4, and then here I'm going from 7 to 3, so that's going to be 4 times the left height of 5. So 4 times 5, I got me at 20, and so we're looking at 24.5 or 24.5. Now, what about the units? Well, what we did was we multiplied these units, which are hours, times these units, which are pounds per hour, pounds of lint per hour. And when we multiply pounds per hour times hours, those are going to cancel. And so what we're going to have then is the total amount, an estimate of the total amount of lint gathered in those first 7 hours. Okay. Now, please do the same problem, but this time do a trapezoid sum. Okay. Please do a trapezoid sum. Welcome back. Can I use the shortcut here? Remember, we had a shortcut that said 1 of the first, 1 of the last, 1 of the last, and 2 of each of the intervening or interior bases. Can I use that here? The answer is no, because that shortcut only works when we have a consistent subinterval width, and we don't have a consistent subinterval width here. So we're going to have to do something a little different. We're going to have to actually do the trapezoid rule. Remember, area of a trapezoid is 1/2 height B1 plus B2. And remember that this is the height, and there's B1, and there's B2. And we have to do it for each of these 3. So I've got 1/2, 1 minus 0 times 1/2 plus 2 plus, that's this trapezoid here. And maybe you'd be happier if I drew it as a trapezoid. Here's our trapezoid. Okay, and then the second one, this one here, is going to also be 1/2. Our subinterval width is 3 minus 1. Base 1 is 2. And base 2 over here is 5. And finally, we've got this last trapezoid, which is that one. And that one's going to be 1/2. The subinterval width is 7 minus 3. And the bases are 5 and 1. Again, in free response, you can stop here. And I would say it's a smart move to stop there because lots of people make little mistakes from here. Okay, now what about, no, not that. All right, so what do I want to do next? I don't want to do that part. Well, let's go and deal with, if you got the exam off okay, I wanted to take a quick look at some exam problems. So, for example, the limit as x heads to -5, x squared plus 3x minus 10 over x plus 5. Well, if I plug a 5 in here, I'm going to have, -5 in here. I'm going to have 25 minus 15 minus 10. I have a 0 on top. If I plug a -5 in here, I have a 0 on the bottom. So I've got an indeterminate form. And we still haven't learned L'Hopital's rule. So we're going to have to do this algebraically, like we did in chapter 2. I'm going to do x plus 5 and x minus 2 over x plus 5. Those cancel. Now I can plug in my -5. -5 minus 2 is -7. All right? I was surprised with people getting that one wrong, and I just chalk it up to people didn't go and study enough. All right, how about this one? H of t equals 128 minus 16t squared. And I'd like to know the average velocity on 1 to 2. And this is height or position, if you will. So, take a moment to do this one. Come back when you're done. All right, so I hope you did s of 2 minus s of 1 over 2 minus 1. That's average velocity. We will have a way to find average velocity using integration and the velocity function. But we don't know how to do that yet. And so we're doing average velocity as the average rate of change in position with respect to time, because that's actually the definition that we talked about last semester for average velocity. So s of 2, I'm going to plug in my 2. 2 squared is 4. 4 times 16 is 64. 128 minus 64 is 64. So s of 2 is 64. What about s of 1? Well, s of 1 is going to be 128 minus 16 times 1 squared, or s of 1 is going to be 112. Yes. Okay, and so here we want 64 minus 112 over 1. Yes, on free response you can stop here. So do I want 48? 48, and do we have units? We don't have units. We suspect that this is feet per second, that this is Newton's gravity thing. But without explicit units, we don't have to worry about them. Ooh, and how about this question dealing with the same function? How fast was it going when it hit the ground? Okay, pause the video, give that one a try. Welcome back. So, when does it hit the ground? Like, I know how fast, I want to know the velocity, so I got to take the derivative of this. But what number am I supposed to plug in? Because I don't yet know when this thing hit the ground. I do know that this is a parabola with an intercept of 128, and it goes down and hits the ground. Hey, that's the x, or in this case t, intercept. So 0 equals 128 minus 16t squared. 16t squared equals 128. And we know that 128 divided by 16 is going to be 8. So I get t squared equals 8, where t equals plus and minus root 8. And that's going to be plus and minus 2 root 2. Okay, so this isn't the negative version. The negative one doesn't make sense in the context of this problem. So we've got 2 root 2. Now that's when this thing hits the ground. but we want to know how fast at that moment in time. So we're looking for v of 2 root 2, which means I need to plug 2 root 2 into the velocity equation. Remember from last semester that velocity is the derivative of position, and so the derivative of 128 is not 128. Please wake up. The derivative here is going to be negative 32t. So I'm plugging in my 2 root 2 in there for that t, and I get negative 64 root 2. And that's how fast it's going when it hits the ground. Negative means down. Okay, good. Next, I was a little concerned with this one. I was actually kind of surprised because this was the last thing we did last semester. Evaluate an integral by appealing to the geometry of the situation. Of course, that does require you to recognize that this is a semicircle. 5, negative 5. But we've looked at these semicircles both in calculus and in pre-calc. So, yeah, you've got to own this. And up here, 5. So, this is a semicircle that goes from negative 5 to 5. We're looking for this area. And so I'm expecting you to say, oh, pi r squared is the area of a circle, and this is only half of that. When the radius is, what's our radius? What's our radius? Our radius is 5. So we're going to have 1/2 pi 5 squared, or 25 pi over 2. Okay? And then what about this one? I mean, talk about surprises. What about this one? I want to find the integral of 2x plus 3 dx from 0 to 2. Okay? Take a moment to try that one again now. I'm interested to see how it goes. All right, so we know the graph 2x plus 3 is this line. It's got 0, 3 for a y-intercept. I want to go out to 2. 2 times 2 is 4. 4 plus 3 is 7. So this is 2, 7. And I want to find the area between the curve and the x-axis. Well, there's a trapezoid for us. You could certainly split this up into a triangle plus a rectangle. But yeah, I'm just going to use the trapezoid formula because I need to know how to find the area of a trapezoid, so stop being lazy about that. All right, there's 2, there's 0, and so we've got 2 minus 0 for the height. Base 1 is 3. Base 2 is 7. So I get 10. 10 is the value of that integral. Okay? Okay. Next. By the way, remember I said you actually need to know all the derivatives from last semester. And some of you weren't even quite clear of them on the actual final exam, and which suggests to me that, yeah, you got to be practicing. You got to be working on that differentiation and integration packet. Remember, 5 problems a day. Perfect. You will time it just right. You will be so ready for that AP exam. All right, so we're asked here to find y prime. Will you find y prime here? Okay, so the derivative of 4 to the is 4 to the times ln of the base times the derivative of that stuff. Then we have this minus, and now the derivative of e to the is e to the times the derivative of that power. Okay? Please don't use the product rule here. This is not a power rule situation. Yeah, I have to know how to do these derivatives. You can, of course, rewrite this as negative 3 ln 4 times 4 to the minus 3x plus 1. Likewise here, you can say negative 8x e to the x squared. That's fine too. Or you can just leave it like that. All right. So that's what well, all right. This was the one that most people had difficulty with on the test. we're told that you want to fence in an area with a little stream along the side. And we're calling this X and Y and X. And you've got 400 square feet here. Area is 400. And what I want to know is the cost. We're given a cost equation, 10y plus 25, 2x plus y. And so I understand that this is a certain number of feet, and this is saying, hey, we're paying $10 for each of those feet. And, oh, it's not a stream, is it? Oh, sorry. No, that's a line of shrubs. That is that. And then these, which are paved, I've got these two X's and this one Y, and I'm paving all of this. Then that's going to cost $25 a foot. Okay? Okay. So I'm asked to find C prime. Well, I don't really want to find C prime with X's and Y's. I would be willing to do this. 10y plus 50x plus 25y, and then c equals 35y plus 50x. And I know we know how to do things implicitly, but no, really, I want to use a helping equation. I know that the area is 400, and I know that area of a rectangle is length times width. So 400 equals xy. I'd like to get rid of y for no good reason. So I'm going to solve this equation for y, 400 over x. So we've got 35 times 400 over x plus 50x. And I want to know c prime. So this is 400x to the minus 1 times 35. I'm going to have 35 times 400 times negative 1 x to the minus 2 plus 50. Okay. Now, we want to find when cost is minimized. So I want to set c prime equal to 0. I guess I have some implied endpoints. Like I don't think we can have any negative costs and zero cost. I don't believe in that one either. I will say that 35 times 400, for the people who are waiting for me to write that in as a number, it's 14,000. So we've got negative 14,000 over x squared plus 50 equals c prime. Well, if I plug in a 0 for c prime, I can then go about solving this. I'm going to add this to both sides. And so I have 50 equals 14,000 x squared. Multiply both sides by x squared. Divide both sides by 50. Okay, so 14,000 divided by 50. And I've got 280. So I know that, dink, 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 280. So x squared equals 280. And if I take the square root of that number, I end up with 16.733. Now you could say you have plus and minus, but no, because I can't have a negative side length in this problem, and that's what x represents. So there's my critical number. When, and I have a c prime sign chart here, when x is 16.733, do I have a max or a min? Well, I'm hoping that it's a min, and that's the answer to my question. We do have this implied boundary here at 0. I don't seem to have a boundary here. And you could say, well, Mr. Google, if this is 400, well, that's going to be 1. But if this is 800, then this is just 1/2. Yeah, so no, I don't have a boundary over here. So let's plug something into c prime, if we can find c prime again. Oh, here's c prime. I'm going to plug in not a 0, because the derivative doesn't exist at 0. And I'm going to plug in a 1. If I plug in a 1 here, I get negative 14,000 plus 50. That's definitely negative. And if I plug in something over here, like 100. Okay, so 100 squared is 10,000. Negative 14,000 divided by 10,000 is negative 1.4 plus 50. That's definitely positive. Okay, so yeah, I've got a minimum when x equals, cost is minimized when x equals 16.733. All right, so I hope that sort of put to rest some of the things that you were frustrated by on that exam. But maybe it's already too late for you to have that sort of understanding. I kind of wanted to go next and say, hey, what's the integral from 0 to 4? 16 minus x squared dx. Will you please do that one? And I hope you were thinking about semicircle, but I hope actually you were thinking about, from 0 to 4, it's a quarter of a circle. So I want 1/4 pi r squared. What's our radius? Our radius is 4. So we've got 1/4 pi 4 squared, and we end up with 4 pi. So this is 4 pi. All right. How about this one? What can you do with this one? Integral from 0 to 3 of absolute value of x minus 2 dx. Luckily, you're amazing graphers, and you know what that looks like. You know how transformations affect that absolute value of x. So, find that integral. Again, though, we're still appealing to the geometry of the situation. So, here's 2, here's 3, and we'd like to find this. So, what's my height over here at 0? Well, if I plug in a 0 here, absolute value of negative 2 is 2, so this is 0, 2. So I've got 1/2, a base of 2, a height of 2, plus this triangle, 1/2, 3 minus 2 is 1. What's the height here? If I plug a 3 in here, 3 minus 2 is 1, absolute value of 1 is 1. Okay, and again, you can stop here. For free response. For multiple choice, you would want to take it further and get 2.5. All right. Now, what about something like this? The integral from 0 to pi over 2 e to the x sine x dx. We'll actually learn how to do this by hand, but right now, I think you need to be doing it with your calculator. Okay. Does that help a little? There we go. All right. So, not n deriv, but I want to go to math, and I want to scroll down until I see function int f int. That's the one for doing integrals, and we want to integrate from 0 to 2. Those of you with new calculators, you see the things to plug into the little boxes, right? You've got this when you do f int, a little box, a little box, a box for a function, and then it says x equals and a box over here. And so you're just going to put these things in there. You're going to put in 0 here, pi over 2 here, and, oh, no, it's this, isn't it? It's d box. There we go. You're going to plug in the function, or you're going to type the function to y1 and put y1 here. And of course, in our class, we're going to put an x there. Okay? In Calc 3, you might put a y or a z there. But for us, it's just always going to be x's. Now, on the old school calculator, I need to provide all that same information, but in this order: e to the x sine x, comma, x, that's this one, comma, a value, comma, b value. Okay, so that's what we want to do. What do I need to check and make sure before I do this, though? Because of the presence of that. That's right, I need to make sure that I'm in the right mode. So let's go over to mode and see, and are we? Yes, we are in radians. You should really be in radians as a standard. So if I do from my main screen, and you should do this too to confirm A, that you get the same answer on your calculator, but also B, so that you sort of start making some muscle memory on how to find this thing. This is one of the 4 things that College Board expects you to be able to do on your calculator. They want you to be able to graph a derivative on your calculator as well as evaluate a derivative with your calculator. They want you to be able to evaluate an integral with your calculator. So with that in mind, let's make sure we can do this. I've got e to the x sine x, comma, there above the 7 key, comma, x, comma, 0, comma, pi divided by 2. And I seem to have had the wrong number of parentheses. Oh, what's that? X? Oh, I see. Gotcha. Yeah. You know, it's funny because in my head I was thinking, don't forget to close that. And I didn't say that to you, and I really should have. And we need to close this one here as well. Insert parentheses. Okay. Bah. Be awake, Kutla. Oh, look, that's not the one. And good. And enter. And so I end up with 2.905. Remember, no rounding until the end. Don't use 1.57 here. Just type it in as pi over 2. And there's our value of this integral. Okay? No one's expecting you to do that by hand in Chapter 6. Please make sure you can do it with your calculator. And so just to practice that, we do this one. 0 to 1 cosine of x cube root of x dx. And yes, they're glued together with multiplication. Okay, so you do it, I'll do it, we'll compare answers. And the function. Don't forget to close that parenthesis. X, 0, 1. And I get 0.127. All right, so that's something we need to be able to do. I think you need to be able to evaluate integrals by appealing to the geometry of the situation. And I want to kind of look at that, but also looking at what we know from algebra. So here, I'm going to give you this integral, and I'm going to say that the integral from 0 to 1 of cube root of x dx equals 3/4. Okay? This is a non-calculator problem. So you just need to, have this piece of knowledge to evaluate all these integrals. So what about the integral from -1 to 1 of cube root of x dx? How could we determine that? No, I wouldn't do something like this where I said 0 to 1 times 2. Not here, no. But I would actually think about this graphically. One of the reasons I had you learn the reference graph for cube root of x is so that when we get to a moment like this, remember we have an undefined slope here at 0. Here's our cube root graph. And this is 0 to 1, and we know this is 3/4. Well, here's -1 to 0. And because cube root of x is an odd function with origin symmetry, we know this is going to be -3/4. And so we know that this integral would be 0, right? Because this up piece will cancel exactly out this down piece, okay? All right, what's next? How about the integral from -1 to 1 of the absolute value of cube root of x dx? I'm definitely not going to be trying something like this algebraically. I'm sorry, I don't want to, no, ew, absolute value. I want to think about this graphically. We've got our absolute value, our cube root of x inside of an absolute value. how does that affect this cube root of x graph? That's right, it takes this whole part of the graph over here and turns it positive. And so now what we want to do is we want to go from -1 all the way out to 1. Well, we know that this area is 3/4. Guess what? This is also 3/4. So 3/4 plus 3/4 is 6/4, not 6/8. Oh, don't say that. It's 6/4, and that reduces to 3/2. Okay? Didn't need to pick up a calculator, didn't need to do a lot of fancy stuff, did have to think about this graphically. Okay, how about this one? The integral from 2 to 3 of the cube root of x minus 2 dx. I know, right? Kukla, what are you doing here? Well, but think about it, and think about it graphically. Here's 2. Here's my cube root of x graph, right? Because we're just taking cube root of x and shifting it right to, and I want to go from 2 to 3. I want to go from here, here. Well, isn't that the same shape as this one from 0 to 1 that was equal to 3/4? Well, yes, it is. So guess what? This is 3/4. Okay? Really, one of the things I like about this class is it really encourages us not to just be like the calculus monkey, churning out derivatives, but to actually think, to enjoy that birthright. I mean, look at all the other mammals whose thinking can't go as far as ours. Be that thinking creature, not the calculus monkey. Okay, how about this one? The integral cube root of x minus 1 dx. Well, let's think about that one graphically. So cube root of x shifted down 1. That's it. Well, now what am I looking at here? Oh, sorry, that's not the right shape. That was x to the 3rd. There, that's our cube root shape. That. And down here. But we only want from 0 to 1. Okay, now, I want to think about this in 2 ways. The first way is visually. We know that this amount from the graphs we've done already today, I mean, we were looking at this and saying 0 to 1, and that's going to be 3/4. And I see that shape here, but it's not between the curve and the x-axis. When I'm looking for the integral, I'm looking for this here. And the way I'm going to do that, at least in this problem, is I'm going to think about this shape minus this piece to leave me with that. Okay, so we know that this is 0 and this is 1, so we know this side length is 1. And what's this value over here? Where are we? How far down are we going? If I plug a 0 in here, I get a -1, so that's -1. So my square here is 1 times -1. Okay, so we've got this is an area of -1. And then we've got 3/4. This is 3/4. So 1 minus, but it's below, so I want to subtract a -3/4. There we go. And so what do I end up with? -1 minus a -3/4 is -1 plus 3/4, or -1/4. Now, some people are really comfortable with that kind of thing, and others definitely aren't. So for those of you who definitely aren't, let's take a look at the problem this way. Okay? Let's split this up. There's one integral minus another integral. We know this is 3/4 by definition, and we remember from last semester how to do the integral of a constant. Remember when we were doing that 60 miles an hour for 2 hours, and we said, oh yeah, we're just going to do b minus a times that constant to find the area of that, and therefore this integral. So for me, it's going to be b minus a times that constant. And so we've got 3/4 minus 1 or negative 1/4. So we can do it that way as well. Okay? You have freedom of choice. Okay. How about this one? Let's just change it a little. Maybe you want to try this one. 1 minus cube root of x dx. Also from 0 to 1. Don't use your calculator, though you may want to confirm the value of this with your calculator. But do, think about it either geometrically or using your calculus integral properties, and come back when you're done. Hey, welcome back. There's cube root of x. This is cube root of x flipped upside down and shifted up 1. So if cube root of x gets flipped upside down, cube root of x looks like that. And now we want to shift up by 1. So shift up by 1. I'm going to be here with my inflection point, and we. So how do I do this? Well, I think this is time to do that. This is 3/4 thing, and this is 1. And 1 by 1, the area is 1 for this whole square. And if we take away that part, we'll be left with this. And so I imagine positive 1/4. Why don't we take a look at doing this with our calculus properties? 0 to 1 of 1 dx minus the integral from 0 to 1 of cube root of x dx. Well, the integral of a constant is b minus a times c. So we've got 1, and here we know this, because it was given to us, is 3/4, and again, I get 1/4. Okay? Okay. Well, how about this challenge problem? Okay, I shouldn't have said challenge problem, because I don't think it's a challenge problem for most of you. But I want to go negative 1 to 1 of 1 minus absolute value cube root of x dx. Okay, so when I think about that, I'm thinking about, well, here's cube root of x. Alexa, off. Here's cube root of x, and in the absolute value. But I want to flip it upside down. And I want to, move it up 1. So here's 1, and there we go, and there we go. And I'm looking for this area. Now, I do see the symmetry here. So I think I'm just going to think about 2 times the integral from 0 to 1. So I'm going to find that, and then double it. Okay? So what's this area? Well, this is 3/4 again. It's that same shape. It's flipped upside down, but it's that same shape. And here I've got what I'm looking for. We know we're inside of this square, 1 by 1. So we've got 1 minus 3/4 is 1/4. All right. Well, I hope that was useful. I hope that helps. Kind of want to give you 1 or 2 other ones, but no, I think that's going to be plenty for today. All right. I look forward to seeing you in the next video. Have a great day, everyone.